Welcome back. Today's lecture we're going to talk about what sets the temperature of planets. Why is Mercury hot? Uranus cold? Why is Venus so damn hot? So let's look at the three parts of our lecture. We're going to begin in the first section with an overview of the law of the basic physics, talking about the temperature, what temperature means, what's a black body, what do we mean when we talk about luminosity. Then we'll use energy conservation to compute the temperature of the planets, and then apply it to see what makes planets habitable. This will be a much more quantitative lecture than the previous lecture. What we're going to try to do is introduce a lot of the basic physics, show how we can use that physics to understand the properties of planets. For some of you who are familiar with this physics, this may seem simple. For others of you who are not used to quantitative reasoning, this may be more challenging. Let me encourage you, if things don't make sense, to go back, listen to the lecture again, work through the underlying physics and algebra, and see what you can understand. I think you'll find it to be very rewarding, because you'll be able to see how we can use basic physical principles to make general statements about properties of planets. So let's begin by reviewing temperature. There are three different temperature scales that are often used. Here in the United States, we use the Fahrenheit scale. That gets a sad face because the Fahrenheit scale's not well adapted to doing much in the way scientifically. It's a funny scale in that water freezes at 32, water boils at 212 degrees Fahrenheit, and absolute zero, the minimum temperature that things can reach in the universe, is minus 459 degrees Fahrenheit. In much of the rest of the world, people use the Celsius scale. The Celsius scale has the advantage of water freezing at zero, boiling at 100 degrees. So we have a nice factor of 100 over which water exists as a liquid. As we think about habitability in planets, this is an interesting range to think about. All life that we know about on Earth requires water. And while it's possible life could exist in another medium, water seems to be so fundamental to life that we often start by assuming that we need to have conditions to have liquid water in order to have habitability. This may be the wrong assumption, but since we only know of life on our planet, when we try to extrapolate to other systems, one of the things we do is start by thinking about whether water could exist. Most physicists don't like to use either the Fahrenheit or Celsius scale, but the Kelvin scale. The Kelvin scale is easily related to Celsius. The temperature in Celsius is the temperature in Kelvin minus 273 degrees. On the Kelvin scale, the coldest temperatures can get is absolute zero. That's the nice thing about the Kelvin scale. You never have negative temperatures. Temperatures start at zero. Water freezes at 273 degrees Kelvin, and water boils at 373 degrees Kelvin. You notice we just have to subtract 273 to go from Kelvin to Celsius. 273 minus 273 is 0, so water freezes at 273 degrees Kelvin. We'll refer back to this diagram later, but it's a scale that I think is important for you to understand because it's going to be much easier to talk about properties of stars and of planets using the Kelvin scale. And of course, we're all familiar with what's hot and what's cold in terms of fire being hot and ice cream being cold. But I also want to remind you, when you think about hot and cold, you should think about the atoms in a gas when it's hot moving very quickly, or when it's cold they move very slowly. When we go to absolute zero, atoms or molecules don't move at all. The next concept I want to talk about is luminosity. Luminosity is the total energy that an object emits per unit time. We can think about a light bulb, emitting light. We describe the energy it puts out in terms of number of watts. A typical light bulb might emit about 100 watts of energy. And since luminosity is energy per unit time, that's 100 joules per second. As I stand here talking to you, my body's also emitting about 100 watts of heat, a comparable number. So you can think about watts as a unit where things that you encounter in daily life, your computer, light, your own body, are emitting tens or hundreds of watts of energy. When we look at the sun emits 4 times 10 to the 26 watts, or equivalently, if I don't want to use scientific notation, 400 followed by another 24 zeros, watts. So that's a lot of light bulbs. So the sun is much more energetic. But still, we want to express this all in the same units. Watts are equivalently joules per second. The light that comes from the sun is mostly visible or near-infrared light. I want to remind you about the basic properties of the electromagnetic spectrum. I think most of us are familiar with the basic properties of visible light, that if we look at a rainbow or look at light through a prism, we can divide light into red, orange, yellow, green, blue, or violet light. The properties of light depend on its wavelength. If light has a shorter wavelength, visible light might appear blue or violet. The wavelengths here are expressed in nanometers, or billionths of a meter. Blue light is emitted at about 500 nanometers. Yellow light, the wavelength's a bit longer, 600 nanometers, while red light is about 700 nanometers. The visible spectrum is but a small portion of the overall spectrum of light. As we go towards shorter wavelengths, we move to higher energies. We can look, and we'll begin with visible, then ultraviolet, then X-ray, then gamma rays. These X-rays and gamma rays carry an enormous amount of energy. Most of them, fortunately, do not reach the ground, because X-rays and gamma rays are absorbed by our atmosphere. As we move towards longer wavelengths, we're looking at less energetic photons. So we can move from the red to infrared light to microwaves to radio waves. Most of the sun's light is emitted at visible and infrared light. The Earth itself is radiating, as is our bodies. Our bodies are mostly radiating in the infrared. An important idea when we look at objects is they emit usually what's called a black body spectrum. So what's plotted here is how much energy is emitted as a function of wavelength when you look at objects of different temperatures. This yellow curve here shows the energy emitted by the sun. The sun emits most of its energy here around visible wavelengths, but you'll notice the sun also emits ultraviolet wavelengths. These ultraviolet waves emitted by the sun is what causes skin cancer. And one of the reasons we put on suntan lotion or try to stay out of the direct sun is to protect our skin from this energetic light coming from the sun that are able to produce mutations in our cells. While the sun emits a lot of its light at visible wavelengths, you'll notice the sun, the yellow line in this plot, also emits a lot of radiation in the infrared. The red curve shows radiation emitted by the Earth. Recall that 0 degrees centigrade is 273 Kelvin. So this red curve at 300 Kelvin, or equivalently 27 degrees centigrade, or Celsius, corresponds to the radiation emitted by the Earth. You can see that the Earth emits very little in this visible range. Most of the Earth's radiation is coming out at wavelengths of around 10 microns. So the Earth is emitting primarily in the infrared. And you can see the characteristic wavelength is a function of energy. as we go from a planet like Saturn to the Earth to Mercury, the characteristic wavelength it emits at moves upwards. Finally, we get to stars like a red dwarf star, the Sun, or a blue star, say an A star. As we move up in temperature, the characteristic wavelength shifts this way towards shorter wavelengths. These curves also show the total energy emitted. And you'll notice there's much more area under the yellow curve than the red curve. The Sun, per unit area, emits a lot more energy than the Earth does. If we want to look at how much energy the Sun or the Earth emits, we want to calculate the flux per unit area and then figure out how much area the Sun or the Earth has. So before we go further, we do a little quick geometry review. Let me remind you that if I draw a circle, the circumference of the circle is 2 pi times its radius. The radius of a circle recalls the distance from its center to its edge. The diameter goes all the way across. The diameter of a circle is twice its radius. So the circumference of a circle is 2 pi r. If I draw a sphere, like the Earth, the surface area of the sphere is 4 pi r squared. And since we want to compute the amount of energy emitted by the Sun or the Earth, we want to compute the energy per unit area, then multiply it by the surface area. Okay, now let's turn to one of the technical parts of this discussion, the Stefan Boltzmann law. If we take this curve and ask how much energy is emitted per unit area by a star or by the Earth, that flux goes as temperature to the 4th power times a constant. This constant, written here, is called the Stefan Boltzmann constant. And this is the flux emitted by the Sun or by the Earth. If I want to compute the luminosity, how bright the Sun is, I take its surface area, I multiply by the flux. Surface area, recall, is 4 pi r squared. The flux is sigma temperature to the 4th. This gives me one of the most important relationships we want to write down to characterize what's going on with a star. The luminosity, the energy a star emits per unit time, depends on how big the star is and how hot the star is. If a star is bigger, it's going to emit more radiation. A red giant star is going to emit a lot more energy than a small little red dwarf star. A hotter star also emits more energy than a cold star, and it's going to scale as radius squared and temperature to the 4th power. This equation will tell us the basic properties we will observe of stars. Just notice, before we go further, just something about constants. You'll notice it's constants in units of watts per meter squared per Kelvin to the 4th power. If I want to compute the luminosity of the Sun, I need to stick in its radius in meters and its temperature in Kelvin if I want to use this equation with the constant expressed this way to compute the luminosity of the Sun. Good. Let's apply this. And let's compute how much energy does the Sun radiate. The Sun's temperature is about 6,000 degrees Kelvin, or to be precise, 5,778 degrees Kelvin. The radius of the Sun is about 7 times 10 to the 8 meters. I can plug this into this equation, sticking in the radius squared, the constant, and the temperature of the Sun. Plugging in these numbers, you'll find that the Sun's luminosity is about 4 times 10 to the 26 watts. Thus, we can relate the Sun's temperature and radius to the amount of energy that comes out. For the problem, I'd like you to apply this to the Earth. So you should now exit the lecture, look up the radius of the Earth, take as its typical temperature about 16 degrees centigrade, or equivalently 289 degrees Kelvin, plug in the temperature, the radius, and compute the luminosity of the Earth, and then compare that to the luminosity of the Sun. See you in a few moments.